So basically at COG, which is a European startup funded with VC funding, we are trying to build real-time AI. That is AI that is 100 times or even 1,000 times faster than what it currently is. So in order to achieve this, we have two streams of research, one on low-level GPU engineering and the other on model architecture, where we design and train our own models. Real-time AI, we believe, is a new paradigm for the future of computing. So imagine if AI was 100 times faster. Project yourself in maybe 2 or 3 years, right? We will generate a lot more tokens. So you perform a request, or a machine, an agent perform a request. They will output not thousands of tokens, but hundreds or even millions tokens. So what will be possible? Well, first of all, agentic workflows come to mind, right? They will take seconds, not hours, so we could have much faster iterations on software engineering. Deep research that is instant. AI scientists will also be able to make great creative discoveries because it will be able to perform experiments and solve problems with reasoning a lot faster with a lot more tokens. And we will have a lot of also domain-specific use cases in biology, finance. Think about reacting before the competitors with a lot of thinking to an earning call, for instance. Cybersecurity, where speed is really important, and the ability to think in order to discriminate between legitimate usage and hackers. But also, intelligence will skyrocket. Why? Because we now know that test-time compute is a critical way to get much better results, much better intelligence, much better accuracy on benchmarks. So you have these scaling laws for reasoning models that prove this. If you output more tokens, you will have much better results. All right, so that's great. But what if AI was not 100 times faster? What if it was 1,000 times faster? We believe it will unlock the next wave of human-computer interactions and experiences. So basically, content will be generated on the fly by AI. Your movie, your app, your video game will be generated by AI and customized, personalized, adapted in real time. So that will be a new way of interacting with computers. Applications will even fix their own bugs interactively, add new feature when you request it. And you will be able to create anything very easily because you will have a swarm of experts, software engineers, product managers, experts in music, video games that will help you in real time and will allow you to iterate and interact very fast with your artifact. So it's great, right? Real-time AI will be incredible. So maybe in 10 years, maybe in 10 years we'll have this. And it will be also, of course, a new era for software engineering because software engineering is basically a lot of iteration where you define what you want to do. May it be a new feature, a bug fix, a prototype. Then you implement it with a nested loop where you think, you act. So you think about how to implement. You write your code, you observe, you run tests, and then you have this loop. And then you reflect. So you act as a product manager, you test what you did, you see if it works, you see if it works for a user, is the UX good, is the UI working, and what's next? You decide what's next, and then you loop. So it's a lot of loops. And even in the nested loop, you have a lot of tokens to output. If you want to refactor something, you will need as many tokens potentially as your original code base. If you want to simulate run traces with a code world model, for instance, you will also need to output a lot of code tokens, and of course, it's a loop. So if AI were a lot faster, you will be able to have basically to unlock the automated AI engineer that will do software engineering for you. So that will be incredible. So is it possible today? Only one way to find out. Let's build it. So first, in order to build real-time AI, we need to choose a metric. So what do we want to optimize for? Usually people optimize for aggregated throughput. So in any communication from a main GPU manufacturer, they say, wow, we are 20 times faster, we put 20 times more tokens, for instance. It's actually aggregated throughput for a lot of requests in parallel. So each individual request is actually very slow. Or it's for prefill. Prefill is when you process your prompt. So you have a lot of flops, a lot of compute, and you process in parallel a lot of tokens in your prompt. So this is about reducing the time to first token, but it's not at all about accelerating the speed of AI, the decoding speed. So what is important for us, for this goal, is the generation speed, which is the decoding token per second for each unique request. So for instance, if you ask ChatGPT for something, it will output at around 50 to 100 tokens per second. So that's great for reading, for a user, a human. But it's not so great when you need to think. Like the thinking models be 2 to 5 minutes before answering. And the pro model take actually 10 to 25 minutes. So not so great. So then you have inference clouds like Fireworks, Together AI. They are doing great job optimizing models on GPU, and they can be faster, but not significantly faster. And then you have people doing dedicated wafer scale chips at Cerebras, or other types of dedicated hardware at Groq, SambaNova, and so on. So this allows to get maybe 10, 20 times faster AI, but there is a bottleneck, and they don't seem to be able to get past around 2,000 to 3,000 tokens per second, even though it's a great engineering. So we set our goal, and our goal is to have 10,000 tokens per second, or even 100,000 tokens per second. Is it possible? To know if it's possible, we first need to choose the right hardware, right? So, of course, we go for dedicated ASICs, like Cerebras. I just talked about it. So, Andrew Feldman, who is a great guy, and he built this incredible company called Cerebras, where they are able to do a full-scale chip of the full wafer. It's a very big chip. And they totally blow out of the water the GPU-based solutions. So it's impossible to do real-time AI with GPU today. They have 21 petabytes per second of memory bandwidth because memory is located with compute at the same location. So it's incredible. But we won't use this. Why? Because, as I said, there are other bottlenecks, like the communication bottleneck. It's a big chip, so at some point you can do local compute, but then you need to have these local computation results communicate together on the world chip. And so you have other types of bottleneck that limit the capacity of these chips. So let's do the impossible, and let's go towards GPUs. Can we beat dedicated hardware with GPUs? So not with consumer-grade GPUs and not with HPC GPUs. Consumer-grade GPU doesn't have enough memory bandwidth, and HPC, they try to focus on stuff like floating point 64, which we don't care about. They try to put together the CPU and the GPU in the same chip. We don't really care about this. So let's go for AI data centers GPU. So when we select a GPU for real-time AI, we don't care about flops. So this is very important. We don't care about flops. So everyone talks about flops. We just don't care. So what we look for high-end GPUs like NVIDIA and AMD GPUs, we look at memory characteristics. And I will explain why just after. So what is important is the HBM. HBM is the main memory of the GPU, how fast it is. The cache is some much faster memory that is on the chip. It can be 3 times faster, it can be 10 times faster depending on where it's located. If it's L1, L2, L3, even faster than that. We care about also the very, very, very fast memory that is on each compute unit or streaming module on NVIDIA. So the GPU is actually a big array of compute units. So on AMD, for instance, MI400X, you have 304 compute units. And on each compute unit, it's able to compute, of course, but also to store data. And they store data in the register file, which is very fast memory, fastest that exists, and local data share, LDS. And when you look at the GPUs through this lens, you can see a very interesting advantage for actually, surprisingly, AMD GPU, or not surprisingly. So the cache size is almost 5 times, more than 5 times bigger, and the register file is also 5 times bigger. So we can exploit that. So we choose this kind of AMD GPU. We remove also third-party abstractions because you cannot get to this kind of speed if you use anything done by others in terms of libraries, programming frameworks that add overheads. So we don't use PyTorch, Triton, intermediate language like Mojo, TinyGrad, ZML, etc. We don't even use the AMD matrix multiplication kernels and communication library because they are too far from the speed of light. So we rewrite everything in low level, in C++ and CDNA free assembly, and we wrote our own communication library called KCCL, which is able to reach communication that is 2 times to 4 times faster than communication from AMD and NVIDIA libraries when you make all 8 GPUs on a server communicate together. We also get rid of the inference engine, VLLM, like we integrate actually into VLLM, so we are fully compatible with it. But if you just use vanilla frameworks, they still have some parts of the inference that run on CPU. And this is impossible because the speed of communication between the GPU and the CPU is low. So you need to have everything, a sequence of tokens that is generating on the GPU without any interruption. And last, we need to define our large language model architecture. So smaller is faster, but we can still be big. Why? So we focus on 2 models. A dense model that has 2 billion parameters. There is a reason why, I will explain later. With 2 billion, you can still have very good AI because you can fine-tune this kind of base models for specific tasks and have them communicate or have some router that choose the right model depending on the task. So it's enough to get great AI, and it's FP8. If we go to FP14, we could FP4, we could go to 4 billion parameters. And we also train a mixture of expert model, which is a 40 billion parameter model. Due to training restrictions, it could actually be a 200 billion or whatever parameter model. So yeah, that's it. We did real-time AI, right? We selected all the right ways, and it works. Not really. You do it, but then you realize it's not right. It sucks, right? Performance is actually very bad. So you need to go hunting every bottleneck that exists. So this is what is actually interesting in this talk. So first bottleneck. You realize on a GPU, you run what is called kernels. Kernels, every little box here, a colored box is a little kernel, which is a little program that runs on the GPU. So for each type of computation, like matrix multiplication, softmax, attention, and stuff, you have a dedicated kernel. But each kernel launch and cleanup takes 4.5 microseconds, which means if you have 10 kernels per transformer layer, because the model is a stack of layers, if you have 25 layers, you are limited by these kernel launches to less than 1,000 tokens per second. So you need to fuse the kernels. So if you go to 10, from 10 to 3 kernels, you actually can reach almost 3,000 tokens per second, which is great, but totally not enough, right? So there is a way, which is to totally remove all kernel overhead by just having one. So one big kernel that will do everything. So the thing is, it's a totally new paradigm for GPU engineering because you have diverse computational shapes in your model. There are diverse matrix sizes and types of computation. And so usually you run each kernel with a specific grid size, which is the number of blocks you run, the number of threads you run per block, and so on. If you want your kernel to be always alive, you need to perform all computations with the same grid parameters. So it's a challenge, but it's possible. So yeah, we did it, right? Of course not. There are other bottlenecks, like the memory bandwidth. So this is the main formula, actually, the main takeaway that is very simple from this talk, is that if we want to optimize for speed for individual requests, we don't care about batch size. We can have low batch size or even batch size 1. And in that case, for each token that you generate, you need to stream, to load all the model weights from the HBM memory, the GPU memory, to the compute unit to perform the computations for all the layers until you get to the token you generate. So that means the tokens per second you can get, there is an upper bound, which is your memory bandwidth divided by how much memory you take. And you take the model, so you have the model size, and you have a KV cache, which is something in Transformer like the history of tokens you generated before. So we won't talk about KV cache because there are ways to limit that, especially at batch size 1. You can do some tricks with attention to compress it, to limit it with Mamba layers, for instance, to do variants of attention, to reduce the KV cache. So we'll focus on bandwidth and model size. So if we look at one GPU, for instance, the MI400X, this is the results we get. We are capped at 2,000 tokens per second because it's the time that the GPU takes to load the 2 gigabytes of a model from memory to the compute unit. So 2,000 tokens per second on GPU, I guess we are still at capped, right? We are not performing better on GPU than on dedicated hardware. So what's the solution? The solution is that on one server you have 8 GPUs. So of course we say, well, let's multiply this number by 8. Let's parallelize the inference of our model on the 8 GPUs. And here the numbers are great. On HBM, you can get up to 16,000 tokens per second. And the interesting thing is that on this GPU, as you saw before, you have an L3 cache that is 256 megabytes. And on 8 GPU, that's 2 gigabytes. So all the model actually can be stored on the L3 cache. So you can get a 3x multiplier by using the L3 cache, and we are around the ballpark of 50,000 tokens per second. So it's incredible, we did it. Except that when you do this, you need for each layer to communicate between all GPUs to all GPUs 2 times. Why? Because if you take a matrix multiplication, if you spread it on 8 GPUs, you split it in 8. So each GPU performs 1/8 of the computation. But then we need to communicate together to add the results to get the final results of the matmul. So even if we are very optimized in terms of inter-GPU communication, it is a hard cap on the number of tokens per second you can get with a standard transformer. You won't be able to go higher than that. So it's impossible to do real-time AI. of course, there is a solution. There is always a solution, but it's a little bit involved. It implies that we change the transformer architecture. So we do what we call the laneformer, which is optimized for parallel inference without any weight for communication. So basically, we change the flow of information in the network, and we need then to retrain these models in order to make them work. But now they are non-blocking. They're still communicating, but they are not waiting for other GPU before continuing computation. So if you do it naively, you have a loss gap and a benchmark accuracy gap between the blue line, which is a very naive 8 lanes parallel transformer, anyway, laneformer, and the Llama 3 model, which is the pink line. And if after a lot of iteration on hyperparameters and the way you do communications, etc., you work a lot on this, like we did, at some point, you have a black line that is almost on the same loss than the Llama 3 pink line. So basically, we are able to have a different model architecture, but which has same loss as training, almost same loss, and similar benchmark results. Well, the full training and the full model is ongoing on scale-weight clusters. So the benchmark result, we don't know yet what will be for all benchmark, but the intermediate benchmarks are looking quite good. There is another issue, which is the L3 cache doesn't work. And so there is a theory and there is a practice, right? So you say, okay, the L3 cache is 3 times faster, it's great. In reality, if you look closely at the hardware, so this is the ML200X GPU, and you can see the purple lines here. It's physical bottlenecks. So basically, the GPU is divided in 4 quadrants, and between these quadrants, which are called IODs, if you want memory to flow through it, it goes through a crossbar where actually it's not big enough, right? You don't have enough flow, enough bandwidth. So if you load memory from an address from the top left, for instance, it has 3 out of 4 chances to be loaded from another quadrant. And then instead of having like 12 terabytes per second of L3 cache, you just get down to like 4.5 terabytes because of these bottlenecks. So luckily, we can find a way. So we try to time the latency of accesses to memory in order to see if we can know for a physical address where it is localized on the GPU. So if I access a buffer, do I know where it's really where the data is stored inside the GPU? And you can see on this table that depending if we are on the same quadrant, on vertical communication, horizontal or diagonal, you have very different latencies. So latency, the time needed for a request to go to memory and come back. So we use this fact to reverse engineer the hashing function that allows the GPU to decide where physically to put bytes on the GPU. So by using latency, you can see here, for specific physical addresses, we can know exactly where it is on the GPU. And we can basically to make sure a compute unit located in one quadrant always talk to memory that is next to it. And by that, we unlock the L3 cache. We have a last issue. The formula is not perfect because on matrix multiplication algorithms, you actually reload some model weights. It's not loaded only once. So when you do A multiplied by B, 2 matrices, maybe B is big and you load it only one time, but A needs to be loaded several times. You will understand why if you do the math. So actually, we are slower than we expect. So we have two mitigating strategies for this, and this two combined allows us to really minimize this to something that is totally negligible, maybe a few percent maximum of the total memory size. So first, you can exploit the cache, right? A2 cache, A3 cache, so that memory that is reloaded is loaded much faster. This is done through careful scheduling of the computation workload on the compute units. And on the MA400, there are 8 L2 cache that are different. So it's a bit involved to exploit this. But you can, if you are low level like we are doing. And of course, the register file is big on AMD, so it's cool because we can load much bigger tiles. And it happens that if we can load much bigger tiles, we will need to load them less often. So the beta factor is lower. So with this, we unlock actually the full memory bandwidth. And of course, there is always another bottleneck, which I will go through in 3 minutes. So the thing is, on the GPU, you know that there are matrix multiplications for doing transformer work, but there are also other types of operations, like grid synchronization, softmax, layer norm, top-k routing for memory, and sampling. These operations do not load model weights. They are just working on data that is already here. And it's an issue because if it takes some time, well, we will be forced to stop streaming our memory. And we don't want that because it will slow us down. So we need to parallelize memory loading and this computation. And to do that, we need this computation to be fast enough. What is our budget? If you load memory in parallel in the local data share, we have a budget of a few microseconds, basically. And it's not really working, right? Because the actual time needed is in the same ballpark. So it's a little bit risky, and some operations are actually taking much more, like green synchronization with cooperative group on AMD take ages. And we need a lot of grid synchronization. Why? Because we fused all our kernels. So basically, when you have two operations on the GPU, like a matmul and a softmax, in two different kernels, the second operation can work on the outputs of the first operation. There is a synchronization barrier that is implicit between the two kernel launches. But if you fuse your kernels, the first computation can happen on different compute units at different times. And so before you can do your softmax or other operation after, you need to synchronize the whole grid, that is the whole GPU, everything on the GPU. And this takes too much time. So we need to rewrite our own synchronization ourselves to make it lower than 1 microsecond. And this is possible because if you look at the latency measurement we made on the various caches, we see if it's on the order of a few hundred nanoseconds to write or load a flag in memory. So by using careful memory channel analysis to avoid contention on memory channels and memory banks, by using an array of flags, and by working intelligently with physical placement, we can get very fast grid synchronization, and we can solve the bottlenecks. Also, of course, we have a big register file on AMD, so actually we could load more data locally, and so we have actually a bigger time budget. And this time is true, we are finished. We did it. So congrats. We even have some room for improvement with speculative decoding, FP4 quantization, or even diffusion. And by using the full HBM and L3 bandwidth on 8 GPU, we are able to achieve our goal of 10,000 or 100,000 tokens per second. So thank you very much. If you have any questions.
Thank you, Gael. I think we can have 2 questions.
Great talk. Thanks again. Quick question. What's the first application that comes to mind to apply the ability to do the real-time AI money?
So the first application is the one we are specifying here at the top of the slide. We are looking for design partners to productize this. So we are French, we do great tech, but we don't know how to do business with it, you know? So, yeah, feel free to talk to me for using our models in your applications, in your company.
Let's talk.
Perfect.
Is there any question? Last one?
Thank you. How you change the ECT part when so how you change the flow of communication for the lane formal architecture?
Yeah, so the lane form architecture. So
I think
basically,
it's a small invention in your part, so I'm so curious how you changed
yeah.
the
So
communication, the ECT part.
yeah, we tried a lot of things. You cannot avoid all communication. I think we need at least one communication, but it's okay to have one. You cannot always eliminate everything. Honestly, I'm a little bit in trouble to answer because we will write a research paper about this, and it's not yet. I don't want to spoil, the exact details right now. But basically, instead of having an immediate communication when you do a tensor parallelism, for instance, instead of having a GPU send their intermediate result directly to other GPU, they can send it, but in the future, basically. So the other GPU will continue working, and when they receive it, they integrate it to their residual stream, they integrate it to their current feature vector.
So it's like a queue.
It's a little bit like a queue where you don't wait for the queue. You just continue computing, and when you have intermediate results for other GPU, which represent information, you integrate this information in your own computation and you continue.